Let's begin now.
Morning sir, Eustaquio here, and in today's video we are going to answer, or I am going to answer, this, the summative assessment 1 of our meter. Here are the instructions. Use an electronic simulation software or multi-simulator to determine what is being asked in each problem. Compare the results using the computed values. So, in the end of this video, we are going to conclude with what are the percent errors of my computed values to the simulated values from the multi-simulator. Submit the recorded video with explanation in the provided SB Dropbox. So, problem 1 is to determine the VO for the network shown in figure 1, this one. And problem 2, determine the VO and ID or the current of the diode for the network shown in figure 2, this one. So, before doing this video, I was able to do the multi-simulated circuit of the problems. So, here we go. This is what I found. On problem 1, figure A, I discovered that the voltage drop, VO of the figure A is 9.31 volts, and in figure B it is 7.02 volts. And in problem number 2, the VO of the first figure, figure A, is negative 4.33 volts, and its diode current is 1.97 milliamperes. And in figure B, the voltage is 6.51 volts, and the diode, the current of the silicon diode is 1.24 milliamperes. So, those are the simulated values, and I will show here my manually computed solution, or my solution for problems 1 and 2. Problem number 1. Here is figure A. Solutions for figure A. To solve the VO, I must compute the problem by using the Kirchhoff's voltage law, or solve it by KVL. So, 20 volts here, the power source, 20 volts minus 0.7 volts of the silicon diode, silicon drop of the diode, minus the germanium diode, or the silicon drop of the germanium diode, which is 0.3 volts. Then minus the resistance of R1 and the R2. There should be an R2 right here, but I forgot to draw it. So, we'll just assume that there is an R2 right there. 2K ohms. So, 20 volts minus 0.7 volts minus 0.3 volts minus 2K plus 2K ohms is equals to 4K ohms times the current. So, what we should do is to transpose this problem, these events, the right side. Then, I use this cool engineering technique, which is to shift solve. So the value that I got, the computed value that I got is 4.75. Yes, 4.75 milliamperes. So that I can compute for the VO, which we are going to use the voltage formula, which is V is equals to current times resistance, VIR. So if the current is 4.75 milliamperes, we will multiply it to the resistance, which is 2K ohms. So VO is equals to 9.5 volts. That is my completed value for problem number 1. Figure B. Figure A. So going to figure B, same as the figure A solution, we're going to use the Kirchhoff's voltage law. So by solving by KVL, we have 10 volts for the power source, 1.2 K ohms for the resistance number 1 there, and plus the 4.7 K ohms to the second resistance, times the current minus 0.7 volts of the diode, germanium diode, silicon diode. So transpose in values to find the answer for the current. So 9.3 volts divided by 5.9 ohms is equals to 1.5763 milliamperes. So we got the value for the current to solve for the VO. So VO. So if the current is 1.563 milliamperes, we multiply it to the 4.7 K ohms or 4,700 ohms of resistance number 2 to get the VO, which is 7.4086 or 7.41 volts. That's the answer in figure computed value that I got in figure B. All in all, in problem number 1, I got on problem number 1 figure A, I got the computed value 9.5 volts. And in figure B, I got the value 7.41 volts for the VO. So going to problem number 2. Here we are asked to solve for the VO and the current of the diode. So in figure A, by using KVL or Kirchhoff's voltage law to find for the VO, this is the solution. Negative VO plus 0.7 volts minus 5 volts equals 0. Transpose negative VO to the right side. Change the sign. VO is equals positive VO is equals to positive 0.7 volts minus 5 volts, which is negative 4.3 volts for my completed value. And for the current of the diode, we are going to use this formula. 0 minus VO divided by 2.2 times 10 raised to the third power ohms, or 2.2 K ohms, 1200 ohms. So if VO is equals to negative 4.3 volts, 0 minus negative 4.3 divided by 2.2 K ohms is going to be equal to 1.955 milliamperes for the current of the diode in figure A. Going to figure B, we are first going to find the current of the diode. So 8 volts minus 0.7 volts minus negative 6 ohms over 1.2 K ohms plus 4.7 K ohms. So compute, we will be getting 2.2542 milliamperes or 2.25 milliamperes. for VO, we are going to, if ID or current of the diode is equals to 2.25, 8 volts minus 1.2 k ohms times 2.25 milliamperes is equals to 5.2949. Then round it off, the VO is equals to 5.295. So my computed values for this, for problem number 2, figure A, is that the VO is equals to negative 4.3 volts, and the ID of figure A is equals to 1.955 milliamperes, and in figure B, the VO is equals to 5.295 volts, and the current of the diode is equals to 2.25 milliamperes. Okay, so now we have the values for the multi-simulator, and we have the value of the computed values from our solutions. So now we can solve for the percent error of our problems. Here. So this is the formula to find the percent error. Computed value minus the simulated value from the simulator over the simulated value times 100%. So in problem number 1, figure A, VO equals 9.31 volts minus 9.5 volts over 9.5 times 100% is equals to 0.02 or 2% error. Figure B, VO is equals to 7.41 volts minus 7.02 volts over 7.02 times 100% is equals to 0.499 or 4.99% error. In problem number 2, figure A, VO is equals to negative 4.3 minus negative 4.33 over 4.33 times 100% is equals to 0.07 or 0.7% error. The ID percent error is equals to 1.97 minus 1.955 or 1.955 times 100%. 0.0076, not 0.76, or 0.76% error. In figure B, VO is equals to 5.295 volts minus 6.51 volts over 6.51 times 100%. This equals to 0.058 or 20.58% error. And the ID of figure B is 1.24 minus 2.25 over 2.25 times 100% is equals to 0.5804 or 58.04% error. So that's about it for my summative exam log, and thank you for watching. See you on the next video.